to talk about today how to do the entire linear programming process. So to do so, I have created two examples that I have filled in that I will walk you through. The first example states 7 members from a local organization are planning on raising money for breast cancer research during the month of October. They have decided to sell handmade tie-dyed t-shirts and woven friendship bracelets. The t-shirts only take an hour to make, but they cost $12 in materials. The bracelets take 3 hours to make, yet only cost $1 in materials. If they plan to each work 6 hours on Saturday to make the fundraising items and plan to invest no more than $84 in materials, what will their maximum proceeds be if they make $5 on each shirt and $6 on each bracelet? So first we start off by listing the two variables. In this case, we're talking about t-shirts and bracelets, which on the left I've denoted by shirts and bracelets. Then reading through the problem, I've identified the two constraints as time and the amount it costs to make it. T-shirts take 1 hour to make, and bracelets take 3 hours to make, and they only have 42 hours total. Shirts take $12 to make, bracelets only take $1 to make, and they only have $84 to work with. To write these as constraints, the rules would be 1S plus 3B has to be less than or equal to 42, and 12S plus B has to be less than or equal to 84. So after I've got my two constraints, I created my t-tables, I found my intercepts, and I graphed them in the graph provided. I tested a point in each inequality and found my feasible region to be the lower left-hand region. Now, what we're adding in today is the rest of the process. So what we do is we first try to decide what the objective function is. Majority of these problems, either you're trying to make money, or you're trying to save money, or it could be about time or materials. In this case, it said we wanted the maximum proceeds. So I just wrote max so it refreshed my mind, is equal to, I get $5 a shirt and $6 a bracelet. Then from there, what you do is we have to pick some ordered pairs in this region to represent answers that would work in this math problem. The problem is there's so many ordered pairs that we have to be more definite on what ordered pairs we pick. So in order to do so, what you do is you take your feasible region and you find its corners. Okay, so my first corner was 0, 0. Then I had 7, 0. I have 0, 14, but this one was kind of hard to read right here. So what I did using elimination is I put my two inequalities together, changing my signs to equal signs, and solved this system of 2. When I did so, I found the ordered pair to be 6, 12, which based on my graph looks approximately what it could be. Then once I have my ordered pairs for all my corners, I plug them all into my objective function. So I plug in the x value, which is the substitution property, and I solve for the y value, which is the maximum value, and what I came up with 0, 84, 35, and 102. Since we wanted the maximum profit, we would choose the 102 as our answer. So the final answer to this math problem is they would need to make 6 shirts, 12 bracelets, and has a proceed of $102. Let's look at one more. This one's about seafood. A seafood restaurant owner orders at least 50 fish. He cannot use more than 30 amberjack or more than 35 flounder. Amberjack costs $4 each and flounder costs $3 each. How many of each type of fish should he use to minimize the cost? So to start with, we start by identifying our two variables. In this case, it's amberjack and flounder. Here we got a couple different rules. We have those single constraints with only one variable in it. It says no Cannot use more than 30 amberjacks. So to say that, I say A is less than or equal to 30. To say more than 35 flounder, it'd be F is less than or equal to 35. Now the only other constraint I have is this 30, which means I can only have, not 30, 50. It says he has to have at least 50 fish. So my total has to be greater than or equal to 50. Well, what has to be greater than or equal to 50? The amount of amberjack combined with the amount of flounder. So that is where I get my three constraints from. Amberjack plus flounder has to be greater than or equal to 50. I have to have less than 30 amberjack. I have to less than or equal to 35 flounder. And my objective function is, it says we want to minimize the cost, but it costs $4 an amberjack and $3 a flounder. So then what I did is I made a t-table and found my intercepts for the first variable, which is represented by the purple line. I tested a feasible region, and greater than or equal to means we're going to go up and to the right. Then I did my amberjack, so I came over here to where amberjack was at 30, and I drawed my perpendicular line. I wanted less than 30, so that's going to go to the left. Flounder, I wanted less than 35, so that's going to go down. So if you look, my feasible region is right in here. Now, to find the corners on this feasible region, some are easy and some are not so easy. Of course, where the green meets the blue, that's pretty easy to find. That is 30, 35, which makes sense. It's where line 30 and 35 cross. But the other ones are not so easy to find. So what I did was I took 30, and using the substitution property this time, I took that point, 30 for amberjack, and I put it in my equation, and I solved for my flounder, which is 20, which makes sense. That's what it looks like. Okay, then I repeated the process, but this time I have 35 flounder. So I put 35 flounder, and I got 15 for my amberjack, which is represented by the blue and the purple's intersection. So this one only has 3 ordered pairs in its feasible region. Then I took each ordered pair and I plugged it in to my objective function, thus yielding me 180, 225, and 165. Now, unlike the last example, we didn't want to maximize, we want to minimize the costs. And the one that provides enough fish for the least amount of money is $165. So the answer to this math problem is, I am going to need 15 amberjack and 35 flounder, which will cost me $165. Hopefully these examples have been a help for you, and you should be able to now complete the linear programming project.